Welcome again. Today, let's do a speed revision of the concepts related to perceptron, artificial neural network, and convolutional neural networks. We will also look at RNN and LSTM. Okay. So, neural networks, as I told in the previous presentation, is a concept that is inspired and derived from uh, how the human brain works. Okay. So we know that the human brain has neurons, and these neurons are connected via what's called as synapses. And the neurons that sort of fire together, they learn a certain aspect. And also, the neurons pass the information from one neuron to the other, right, based on certain activation, right. So firing of a neuron itself is again dependent on whether that input crosses a certain threshold or not. Okay, so if the input, let's say, crosses a certain threshold voltage, which will be of very what to say, like very tiny voltage levels. So if that input voltage crosses a certain threshold voltage, then that neuron would fire. Otherwise, it would not fire. Right. So similarly, in the case of a perceptron, if you look at it, a perceptron is the simplest form of a neural network. Okay, so it forms the foundation, right, on which larger neural networks are in fact built. Okay, so how this works is the perceptron takes an input, right, and it multiplies the input by uh, weights, right? Weights meaning by, so you give certain importance, right, to certain inputs, right? How much importance you give is what is decided by the weights. Okay, and then there is going to be a bias, which we will see in a bit what it is. And so the input is multiplied by the weight, and then and bias is added, and it goes through an activation function, and finally you get an output which is binary, can be a 0 or a 1. All right, let's see how this whole thing works. Right, you see this diagram here. If you look at it, x1, x2, x3, etc. dot dot xn are the inputs, okay, that are provided to the perceptron. So this circle, you can think of it as a, say, a perceptron. um, Say, or maybe a neuron, right? The whole thing we call it as a perceptron. So here, the in W1, W2, W3 that you see just over these lines are the weights. So these inputs are multiplied by these weights, right? And then there is a summation that happens, sigma. So x1 w1 plus x2 w2 plus x3 w3, so on and so forth, and it gets added to a bias b, right? So this bias ensures the summed value, right, that comes out of this say neuron is never 0. All right. So, say for example, if sigma is 0, B will ensure that there is some value over there. So that's the bias. So um, this entire output that you get from this summation and the addition of the bias goes through a activation process, right? So this activation process produces an output which is a 0 or 1. Okay, it's a binary output, yes, no, sort of a thing. Okay, so we will look at an example, and this will become evident. But before we do that, we can formally write the perceptron architecture as a mathematical formula as follows, right? Y is a function of, so this sigma 1 to n, right, wi xi plus b. Okay, and the activation function, right, which is say the f of z, will produce an output of 1 if s is going to be greater than or equal to 0, Otherwise, it will produce an output of 0. Okay. And these weights and the bias that we saw are things that the perceptron will learn, right? And so we can actually adjust these weights, okay, and the biases. Okay, that depends on the kind of class, or the kind of say classification that we are dealing with. Okay, we will see that with a simple example here. Okay, then it will become much more evident to you. So here, let's say the weights W1 and W2 are equal to 1 and the bias is minus 1.5. And what we are going to do is we are going to say build a perceptron that can learn and it can produce an output like an AND gate, right? You know, an AND gate will produce an output of 1 only if both the inputs are 1. You know that. That's the logic of an AND gate. So now, let's say the inputs, right, are x1 and x2. There are two inputs, x1 and x2, and the corresponding weights for W1 is 1 and W2 is also 1, and then the bias is minus 1.5. Now, if you apply this formula, okay, to this example, what you will have is, say, W1 x1 will be 0 times 1 will be 0, and W2 x2, that again will be 0. And when you add this sigma of, say, W1 x1 plus W2 x2 will be 0 plus 0, and then you add it with the bias. So in this case, the bias is minus 1.5. So you get the value of minus 1.5. Okay. And the next case is 0 and 1. If the input x1 is 0 and x2 is 1, then you will have 0 times 1 is 0, then 1 times 1 is 1. So you'll have 0 plus 1 here minus 1.5, that will be minus zero point 0.5. And for the 1 0 case, again you get minus 0.5, applying the same logic. Then for this case, 1 plus 1. So if x1 is 1 and x2 is 1, you get 1 plus 1, that is 2, and you have minus 1.5, that's equal to 0.5. So now applying this logic, okay, so now because z is greater than 0, the output will become 1. So then you can very well understand and see that for a given input 1 and 1, the AND gate in fact will produce an output of 1, and that's exactly how what you get here as well. So now, what are the practical real world use case of this? So, I mean, a perceptron itself, I would say, is a concept which helps you understand and build further uh, based on this understanding. But perceptron itself may not be very useful. Okay, so but nevertheless, if we have to talk about some examples, like you take this example, right? So where you want to say find out whether you can approve a loan or not for somebody, then you could use this. Say, for example, if the income is high and if the credit score is good, then you say that maybe you can give the loan to that person. Okay. And if not, then you're not going to give. So these kind of classifications can be done using this perceptron. And as I told you before, this forms the foundation upon which the other advanced artificial neural networks are built. So it is important that we understand how a perceptron works. Okay. The perceptron also has certain limitations, right? So it's very simplistic. So it can probably only understand and then draw uh, a straightforward boundary, right, between classes, right? So it's like a binary, okay? And because it doesn't have hidden layers, what happens is uh, it can't actually do advanced learning, okay? So for now, just stay with me and try to understand what I'm trying to tell. And these things will become even more clearer as we proceed, right? So more the number of layers, better will be the ability of the neural networks to understand the context and make decisions. Okay. So here you don't have any layer. There is just only one layer, so the capability of this particular neural network to understand and then make decisions is limited. Okay, and of course it cannot, for example, understand non-linear pattern that might exist, on the data. Okay, so basically you can say that higher order thinking, if you have to put it simply, is missing. Okay, it can't really learn and then to predict. Okay, and so that's pretty much about the perceptron. Now let's move to what is called as artificial neural networks. All right, so again, this artificial neural network is nothing but a network of interconnected neurons. So, in the previous example, we looked at only one neuron, but here you're going to have multiple neurons, and these neurons are also going to be interconnected, right? Connected to each other, and they're going to be arranged in layers, right? Um, so we will look at the architecture, right? So it will have an input layer, and it will have a hidden layer, and it will have an output layer. So let me directly go to this diagram. So if you look at it, here you have one, two, three neurons, and in this layer called layer one, you have four neurons, and layer two has four neurons, and the output layer has two neurons. So overall, if you look at it, there are about 4 plus 4, 8 plus 3, 11 plus 2, 15 neurons in this. And so between, say, the input layer and the layer one, if you see, each neuron of the input layer is connected to every neuron of the hidden layer, right? So you can see that, right? So this has one, two, three, four connections, right? This particular neuron. Likewise, this will have four, and this will have four connections. All right. So we call, let's say, the input layer is called as an input layer, and the layer one is also called as a hidden layer, right? We call this as a hidden layer one, this as hidden layer two, and then finally there is going to be an output layer, right? So it's not that you should have only two layers. Okay, for this example we have only two layers, but you can have more than two, maybe 30, 40, 50, 100 layers. These are all pretty common depending on the model that you are going to build. So you will have that many hidden layers. Okay, as I told you, more the hidden layers, better will be the ability of the neural network to learn and comprehend. Okay, so each hidden layer, in fact, learns a certain aspect from the input. Like, to, for example, to give a very, very crude example, right? If you have to, let's say, give an image of a cat, like this, let's say, right? So, um, this is sort of resembles a cat, right? So if you have to feed this to a neural network, and if you want the neural network to identify and tell whether it is a cat or not, maybe the first layer, right, will focus on, say, these lines, right? It will focus on these. It will try to extract these lines or these patterns. Okay, and the second layer might be comprehending based on these circles and these lines, right? There is a circle and there is a dot, and maybe there is a ear, and then it will start extracting more information, which is hierarchical in nature, and it will try to make sense out of the given input, right? For example, as I told you, the first layer may only extract the boundaries of the circle, these say these lines, and then whatnot, and the second layer will put all these things together and it will try to make sense out of what it could be. Okay, it will say maybe these two dot means eyes, and this say triangle probably means an ear, etc. It will try to extract or conclude, right, in that fashion at this layer, and finally it will produce an output. So basically each layer is trying to focus on a certain aspect, and it is trying to learn that and pass that information down to the further layers, so that you can put or assemble all these information together, and then make a final decision or an inference. Okay, so that is what is happening in this case. So what you have to understand is there are multiple layers, and each layer has certain number of neurons, and the neurons. So between the adjacent layers, they all connect to each and every neuron, right? So you can imagine the if the number of layers are more and more, then you're going to have more connections. Likewise, if the number of neurons in each layer is also uh, if they are more, then you're going to have that many connections. Okay, so as you can see, it's already getting a bit complex in terms of the computations that one has to do, right? So we know the inputs are multiplied by weights. So in this case, let's say you have w1, w2, w3, w4. So then you're going to take this, right, input, multiply by w1, then w2, then w3, then w4, and then add it. And similarly, you're going to take this input, then again multiply by w1, w2, w3. So you can easily identify and understand that there are going to be many more computations than what you saw in the case of a single perceptron. Okay, so it's going to get mathematically a little bit more complicated. Okay, so so how the artificial neural network learns, right? So what is that you are actually learning, right? What is that the artificial neural network is learning? So basically it learns these weights and biases, right? I told you when discussing about the perceptron. These weights and biases are the ones that actually these and learns, right? What we actually do is the first step is called as forward propagation, right? In this case, the input flows through the network to produce an output prediction. Let's call it as y cap. Okay, so to start with, you might have some random values for these weights, okay, because it's not known, okay, what value to have for the weights, you may not know. So you start off with some weight and do the forward pass, okay. So and you get an output. Now let's call that output as y cap. So now this is the output produced by your model. Okay, so we will call it as actual output. Now you know the expected output, right? Let's say um, what you do is, and we call this as true value or the expected output as y, right? It's also called as true value or ground truth, right? The actual one, right? The expected one. So the actual is what is the model is producing, and expected is what you are expecting. Now, what you do is you calculate the loss, right? Compare y cap to the true value using a loss function. Okay, so that is nothing but y minus y cap now whole squared by 2. That will be the loss. And then what you do is now you need to make up for this loss, right? Now you go back and you have to now maybe fine tune the weights once again, so that you get the expected output. Okay, but now how do you adjust the weights, right? That happens through a process called as back propagation, right? So now that process lets you complete how much each weight has contributed to the overall error, right? So now this last calculation gives you the error. So now you have to know how much each of the weight has contributed to the error that you are seeing, right? That's the process called as back propagation. And what you actually do is, so you have the weight and you have a eta, right, which is called as a learning rate. Okay. Now this eta is multiplied by the partial differentiation of, so dou L by dou W. So you are basically trying to understand uh, how much each of the weight has contributed to the overall loss, right? That's what happens here, dou L by dou W. And then the value is taken, and then you kind of go and update the weights, then again run the whole process, right? Step 1 to step 4, then look at what is the loss, and then again update the weights until the time your actual output matches the expected output. You go through this process, and once that's done, you have your finalized weights. And this whole process is what is called as learning, right? So generally this learning happens in a compute intensive environment, like say in a cloud, using GPUs. And once the learning process is complete and the weights are finalized, we say that the model is now mature and the model can be deployed, right? What is the meaning of deployed? That means this model can infer now, right? It has learned and it can now infer and produce the outputs, right, in a somewhat faithful fashion. Okay, so there are two steps here. One is learning, the other one is the inference part. Okay, generally inference involves lesser compute than say learning. So and also, as you can already identify and understand, the process of learning involves feeding a lot of data and fine tuning the weights. Okay, so that's something that you may have to understand here. And let's move ahead. So what are the strengths of ANN? Okay, so ANN, unlike Perceptron, can now understand the linear, relationship that might exist in data, and it works for not just only classification like Perceptron, but it can do what is called as regression also. Okay, so I'll tell you what is it with an example, and because you can actually fine tune the depth, width, and the activation choices, we say that the architecture itself is flexible, right? For example, you can have more and more layers, you can have more number of neurons, and you can fine tune the model depending on how much accuracy you need and the application for which you are developing the model. Okay, so let's take this example of classification and regression, right, where ANN can be seen in action, right? One is, let's say, handwritten digit recognition, right? So the input could be given in terms of, say, certain number of pixels, say a 28 cross 28 image, and ANN can learn the strokes, curves, loops, etc. And so for that you have to have hidden layers, right? You can have a layer that learns the strokes, and then the curves and the loops, and then maybe some more layers which will try to predict what that handwritten, say, a particular digit will be. So typically, the output layer might have about, say, 10 neurons, and you would use an activation function called as softmax. So basically, the softmax is an activation functions which will give you a probabilistic distribution, right, as an output, right? So for example, it'll give you a probability for each of the digit, right? So that will range from 0 to 1. Okay. So if it says 0.8, let's say I give as input, let's say something like, say something like this. And if it outputs a probability of zero point 0.8 for 5, then that means then it is, say, 80% confidence, right? In this case, if it is, let's say, 0.96, then that's 96% confident that the input digit is 7. So this is how a classification happens. And in the case of regression, So you can pretty much take this example, house price prediction, right? So input is square feet and the number of bedrooms, and then the location and the age of the building, etc. When you give, so there can be more layers, right? That learn certain features, right? How all these, say, the inputs interact with each other, and then finally you could have. um a number, right? Which is, let's say, a continuous number, okay, not a probability. And it can give you a value, right? Saying, okay, so this is this property given the square feet, bedroom, location, score, age, etc. And it takes maybe a few more things into the context and it predicts. Okay. Similarly, if you look at it, the mileage prediction or the estimated time of arrival prediction by your Google Maps, etc., right, will also use ANNs. Okay. So that's about the regression aspect. Okay. So now, uh, the key difference between classification and regression is classification produces probabilities that sum to one, right? And you use softmax and sigmoid kind of activation functions. And in the case of regression, so it gives you unbounded number like this, right? It's not a probabilistic value that range from 0 to 1. So this is going to be a continuous number. Okay. So what are the limitations of ANN? So does ANN solve all problems, or can it be applied for all kinds of predictions? No. So the problem is because the neurons are all fully connected, right? So what happens is the more deeper the number of the hidden layers get, so the it becomes very very expensive to train the weights and the data, and also to train, right? You need more and more compute, and larger the number of parameters, the more complex the whole computation is going to get, and more costlier it's going to get. And the process of training also will become more and more slower if there are more parameters. Okay. And so there is also a problem of overfitting, wherein high capacity can memorize training data, right, instead of generalizing. So that's basically we call as overfitting. And so it has certain detrimental effect which we will see later. Okay. And this is ANN is also not ideal for image processing, because image, if you look at it, it has many hierarchical aspects that are there. Okay. So in an image, right, so it will have a texture, it will have a color, it will have lighting, it will have shapes, and so on and so forth. And so understanding each of that, and then trying to make sense out of that image, let's say in terms of, say, object recognition or object tracking, etc., then ANN becomes very very complex and not very suitable, okay, for doing such things. Okay. So we will that's where CNN, convolutional neural networks, come into picture. And we will see that in a bit. So let's keep working on this. Yeah. So these are the limitations of ANN. And so basically, as I told you, it it becomes computationally very expensive. Okay. And also the training becomes pretty slow because you have to go back and forth, and there are going to be more and more parameters. Then the problem of overfitting happens, where it kind of sticks to mostly the inputs or the training data it has seen, and it tries to not predict correctly, okay, over a period of time. So that's overfitting. And as I told you, because the images tend to be hierarchical, it's also not ANN is not suitable for image processing. Okay, and of course, it's also not suitable for audio processing because audio is, say, audio or voice, right? Is also um, time series data. Okay, so that calls for remembering not just things spatially, but in terms of time. What came, say, if I'm saying a certain thing. Then in order to understand what I'm saying now, you have to have a context of what was said earlier, right? So, in order for you to understand that, some amount of memory is needed. So, ANN is again not suitable for that kind of a processing, and that's where we have other neural networks like, say, RNN, which is called as recurrent neural network, and then long short-term memory or LSTM, okay, which is suitable for audio and time series data. And CNN, which is convolutional neural network, is pretty common when it comes to image processing, right? Object recognition and object identification and all those things. It's also heavily used in, say, things like self-drive car and computer vision, etc. So we will learn and understand more about CNN and RNN in the next session. I thank you very much for listening. Thank you.